All right, let's start. We have integral from 1 to infinity, 1 over x ln x dx. We have the interval of integration to be 1 and infinity, and that infinity makes this integral improper. But not only that, we have 1 over x ln x, the integrand, being discontinuous on this interval. And the problem point here is the lower limit because ln1 is 0, and 1 over 1 times ln1 is going to shoot you off to infinity. Okay, we have two different things going on in this problem. We have to be double cautious. And if I were you, I would just have my TI-84 with me at this moment and try plotting 1 over x ln x from 1 to a large number because you can't really input infinity when you plot. So choose a large number, 10, 15, whatever, and see what kind of area you have between the graph of 1 over x ln x and the x-axis. Okay, so first that's the first thing to do. And in fact, I have done that here, so I can share that with you. So here we go. I have the blue graph, blue curve, representing the graph of 1 over x ln x. And as I said, 1 is a problem point. In fact, 1, x equals 1, is a vertical asymptote. Okay, is a vertical asymptote. Okay, we had gone through this in Calc 1. This is a vertical asymptote. Okay, so what we should do is since there is like infinite area here going in this direction, we have to be double cautious, and we have to use one of the recipes to handle the left limit. But also, this interval of integration is 1 and infinity, so the other limit is infinity. So going in this direction here, okay, you have infinite area as well. So infinite area as well here. You have infinite area, infinite region. Let's put it like infinite region maybe. That's even better because we don't know the value of the area, right, at this moment. So it's better to call it like just region, because we're going to calculate the areas. Well, the whole area, obviously. It's the area of the infinite region. But let's go back to one of the recipes that we had here. So if you have the lower limit making the function discontinuous, well, we're in this case, right? So then we just replace a by c, and we pass the limit as c approaches a from the right. Okay, that takes care of the lower, in fact, not the lower limit though. Let's see what discontinuity is. Yeah, exactly. Yep. And then we had also another recipe here that if you have one of the limits involving infinity, and in this case our upper limit is infinity, so you replace that by b, and then you pass the limit for b approaching infinity. Okay, so also we have to split this integral into two parts, because what I want to do, and probably you should do, what you should do for questions of this sort, is that you should split this area into two parts. Let's say like I split at right here. So now I have the improper integral of the first kind here to represent this area, right? And to represent this area, I have the improper integral of the first kind, because the limit, one of the limits is infinity, okay? So I would just split this in this region into two parts so that I can attack each part separately. And the question is like, where should I split, right? And I'm going to go with x equals e to do that, and that's my next slide here. So that right at x equals e, I split the region into two parts, as you see. This way, we have two different integrals. And why did I pick e? Because e is a very nice number going along well with ln function, right? So ln e is equal to 1, right? So when I do evaluations later on after the integrations, right? So this will help me. So it doesn't matter. You can go with, if you want, instead of e, you can go with 2, okay? So it again does not matter as long as it's something bigger than 1 and it's not too big. You're good to go, okay? So going back here, I'm going to rewrite this integral as limit as b approaches 1 from the right, okay? Integral b to e, okay? 1 over x ln x dx. And then I have the limit as c approaches infinity, okay? That's good. From e to c, 1 over x ln x dx, okay? Essentially what I did here is that I split the integral from 1 to infinity to integral from 1 to e and e to 1. E to infinity, I'm sorry. So this way I treat this integral like this with this limit, and then I treat this integral with this limit. Okay? So let me just clean this part. I hope you got this part sorted out. And all I need is the antiderivative of 1 over x ln x. So why don't we just work on that on a scratch space, okay? So dx over x ln x. So this is a good application of integration. So use any known technique that we learned earlier. I think this is a good u substitution question. And at this moment, please pause the video and maybe just go through this by yourself. All right. So, but let me just give you the hint. It's a u substitution problem, and u equals ln x. U equals ln x. Okay. So u equals ln x and du equals dx over x. Okay? And this is nice because dx over x is already over there, so du over u is what the integral looks like in the variable u. Okay, that is integrated as ln of u, absolute value of u plus c, and that is equal to ln of ln x plus c. So inside the absolute value, it's ln x. Okay? So once you take care of this indefinite integral, providing you the antiderivative of 1 over x ln x, I can go ahead and then put those back into the limit formulation. All right, so I just copied those antiderivatives back into the limits, and then now let's evaluate the upper and lower limits. I want to use one bracket for each limit. So it's ln of ln e minus ln of ln b. And that takes care of the first limit. And as c approaches infinity, this is ln c minus ln e. Okay, so you will see the advantage of picking e as the middle point in the area, because all of these calculations are going to be very easy right now. In fact, ln e is 1, and ln 1 is just 0. Okay, so this term is going to be 0, as well as this term. These are like terms, right? Okay. Let me just erase this portion here, so I'll continue right from here. Okay, so here we go. So what are we left with? You have minus ln b. And then you have the limit as c approaches infinity, ln c. In fact, let me just write this with ln of ln c, right? There we go. All right, so why don't you think about this limit for a second, because this is our now playground. We converted everything into this limit problem here. So as b approaches 1 from the right, ln 1 plus, so this part of the integral, this part of ln, I'm sorry, is going to tend to 0, but you're on the right of 0. ln, and ln 0 is going to take you to minus infinity. Okay, you can grab ln x and see like as x approaches 0 from the right, the corresponding values tends to minus infinity. So you have minus minus infinity. So this is this approaches minus infinity. Okay, or plus infinity. I'm sorry. This is already minus infinity, right? This whole thing. So minus minus infinity plus infinity. Okay. All right, how about the other one? Well, ln c approaching infinity is going to approach infinity, and ln infinity is going to approach, obviously, infinity. So this whole thing approaches plus infinity. That makes it doesn't exist, obviously. Does not exist, but this makes this integral diverges. And it diverges to infinity. And as you see that both integrals diverge to infinity. That's interesting because we had two infinite regions here, and as you see that this area turns out to be plus infinity as well as this area, and the sum of these areas would be also infinity. But it's a good observation here that you have the infinite region ending up with the area being plus infinity, and same as here. These are two different infinite regions, but turned out to be like they have the area infinity. So that makes the whole area, whole green shaded region, having the area infinity. Okay. All right, I think that's the end of the whole part D, but that's the end of the whole exercise. So I'm gonna finish it here. Thanks for watching. I'll see you in another video. Bye.